And maybe a little mind-bending area of physics, high-spin particles. Specifically those with spins of 7-halves, 9-halves, and maybe even higher.
Right. And your first thought might be, do those even exist? Which is, a perfectly reasonable question to start with.
Exactly. So our mission here is to explore what physics actually tells us about these high-spin entities based on, well, what we know right now.
And it's really important to tackle that existence question straight away. The interesting thing is we don't currently know of any elementary particles.
Yeah.
The fundamental ones in the standard model that have spin 7-halves or 9-halves or anything higher in that half-integer series.
So no fundamental particles like electrons or quarks have these spins.
Correct. And no experiments have found any fundamental particles with these spins either.
Okay, wait. So if they aren't fundamental building blocks, why are we even talking about them? Why are they interesting?
Well, that absence is actually part of what makes them interesting when they do show up elsewhere. We mainly see them in two contexts, which is what we'll focus on.
Okay.
First, as composite particles think highly excited, energetic versions of particles we know better. And second, within some pretty interesting theoretical ideas that might hint at physics beyond the standard model.
Gotcha. So composite particles first. These would be things made up of other things, like protons and neutrons.
Exactly. We'll be looking at how these high spins appear mostly as excited states of baryons. Just a reminder, baryons are particles made of three quarks, like protons and neutrons.
Right, the stuff nuclei are made of.
Precisely. And then we'll touch on the theoretical side, the frameworks that try to make sense of these high spins, or even predict them in certain scenarios.
Okay, let's kick off with spin-7-halves then. You said these are mostly excited baryons.
Yes. Primarily, they're observed as highly excited states of protons and neutrons. You can sort of picture it like an atom absorbing energy, and its electrons jump to higher energy levels.
Okay, like an excited atom.
Kind of like that, yeah. These baryons, made of three quarks, can get into these energetic configurations where their total angular momentum, their spin, adds up to 7-halves.
So it's the same basic particle, just spinning differently or more energetically.
In a way, yes. It's not a new fundamental thing, but a specific high-energy arrangement of the quarks inside. The key is combining the quarks' own intrinsic spins, they each have spin 1/2, with the angular momentum from them orbiting each other inside the baryon.
Okay, so spin plus orbital motion adds up.
Exactly. It all has to add up quantum mechanically to give that total spin of 7-halves.
And are there actual examples of these? Have they been cataloged?
Oh, yes. The Particle Data Group, which is basically the official record keeper for all known particles, lists several. For instance, there's the N2190 resonance.
N2190. So the N means it's related to nucleons, protoneutron. And 2190 is its mass.
Roughly, yes.
Right.
Mass around 2190 MeV cores, and its properties are listed as spin 72 with negative parity.
Negative parity, right. That's about mirror symmetry behavior.
Correct. It's another quantum number that helps classify it.
Right.
There are also delta resonances. Those are baryons made of up and down quarks too, but with a different internal spin configuration examples. They're around 2300 or 2400 MeV-cc that also have spin 7-halves. Sometimes with positive parity, sometimes negative.
Okay. And I remember reading these things are incredibly unstable.
Extremely. Their lifetimes are unbelievably short. We're talking on the order of 10 to 10 nanoseconds. They decay almost instantly via the strong force.
Wow. That's incredibly fast. So if they vanish that quickly, how on earth do scientists measure their spin? How do they even know they were there?
That's a great question, and it's tricky. They don't see the resonance directly. What they do is smash particles together in experiments, say pions hitting protons.
Okay.
Sometimes, in that collision, one of these resonances gets formed very briefly as an intermediate step before it decays into other particles, like maybe a nucleon and some pions.
So you see the decay products.
Exactly. You measure the energy, momentum, and angles of those outgoing particles. Then comes the really clever part. Partial wave analysis.
Partial wave analysis sounds complicated.
It is. It's a sophisticated technique where you analyze the angular distribution of those decay products. How they fly off tells you about the quantum numbers, including the spin of that intermediate state that produced them.
So the pattern of the debris tells you about the explosion, essentially.
That's a good analogy.
Yeah.
But as you can imagine, the higher the spin, the more complex the patterns, the harder the analysis. And if you have multiple resonances with similar masses potentially overlapping,
it gets messy.
It definitely gets messy. There are always uncertainties, especially for these very short-lived, high-spin states.
Okay, so experimentally challenging. What about theoretically? How does the quark model explain getting up to spin 7-halves?
Well, within the standard quark model, like we touched on, you combine the intrinsic spins of the three quarks and their orbital angular momentum, which we often label L.
Right.
The three quark spins can combine to a total quark spin S of either 1/2 or 3/2. To get a total spin J of 7/2, well, you need some orbital motion.
How much?
If the total quark spin S is 1/2, you need quite a bit of orbital angular momentum, L3, to reach J72. If S is 3/2, you could get J72 with L2, or LL3, or even L4, depending on the coupling details.
So the quarks have to be whirling around each other quite energetically.
Essentially, yes. It implies a significant amount of internal excitation.
And can we calculate this from first principles? Like from QCD, the theory of the strong force?
In principle, yes, using lattice QCD. That's where you put the equations of QCD onto a sort of computational grid and solve them numerically.
Right.
But it's computationally extremely demanding, especially for these highly excited states with lots of orbital angular momentum. The calculations become very complex and expensive.
Okay. Now, you mentioned earlier we don't see elementary particles with spin-7-halves. Why not? The source mentioned things like unitarity, causality.
Right. These are really fundamental principles that any sensible quantum field theory, our mathematical language for particles and forces, needs to obey.
Can you give us a quick sense of what they mean?
Sure. Unitarity roughly means probabilities add up correctly. You don't lose or gain probability overall. Causality means effects can't happen before their causes. Renormalizability is a bit more technical, but it's about making sure the theory gives sensible, finite predictions, even when you consider quantum effects at very small scales.
Okay, basic rules for a working theory.
Exactly. And the problem is, when you try to write down theories for interacting elementary particles with high spins, like 7/2, it turns out to be incredibly difficult to satisfy all these rules at the same time. The theories tend to break down in one way or another.
So it's a fundamental theoretical roadblock, not just that we haven't found them yet.
It seems to be a very deep theoretical problem, yes. Especially within the framework of relativistic quantum field theory as we currently understand it.
And there was also this Weinberg-Witten theorem.
Yes, that adds another layer of constraint. It places limits on massless particles with high spin.
Massless, like the photon or potentially the graviton.
Right. The theorem states, basically, that a massless particle with spin J greater than 1 can't have a well-behaved interaction with gravity related to its stress-energy tensor. And a massless particle with spin J greater than 12 can't carry the kind of conserved charge associated with forces like electromagnetism related to a conserved current.
So if high-spin particles were massless mediators of forces, they'd run into trouble with this theorem.
Pretty much. It strongly suggests that fundamental force carriers are limited to lower spins, like spin 1, photon, WZ, gluons, or potentially spin 2, graviton. It makes fundamental high-spin particles, especially massless ones, seem very unlikely in our universe.
Okay, that's a lot on spin-7-halves. Mostly excited baryons, hard to see, hard to calculate, and theoretically problematic if fundamental. What about cranking it up further to spin-9-halves?
Well, it's largely a similar story, just more so. These are also seen as even more highly excited baryonic resonances.
Even higher energy, even shorter lived, presumably.
Generally, yes. The particle data group does list some candidates, like maybe an N2700 or a Delta 2420, both potentially having spin 92 and positive parity. But the evidence is often less clear-cut. The uncertainties are bigger compared to the 72 states.
Makes sense. Harder to produce, harder to pin down, and theoretically, inside the baryon, you'd need even more orbital angular momentum.
Exactly. To get to 9/2 total spin, you need even higher L values in the quark model. For instance, if the quark spins add to S12, you'd probably need L4. If S32, you might need L3, 4, or 5.
So these things are really spinning internally. Now, the outline mentions something called Reg trajectories here. How do they fit in?
Reg trajectories. This
Yeah.
is a really neat concept for organizing this whole zoo of baryon and meson resonances.
Organizing the zoo. I like that. How does it work?
What you do is you plot the spin of the resonances against their mass squared. And what you find, remarkably, is that families of related particles, same quark content, same basic quantum numbers, just different levels of excitation, tend to fall on approximately straight lines.
Straight lines. So spin increases roughly linearly with mass squared.
Yes. So you might find a trajectory that includes a spin 12 state, then a spin 32 state at higher mass, a 52, a 72, and yes, maybe a 92 state, all lying more or less on the same line.
Wow. So it suggests these are all related, like rotational excitations of the same basic thing.
That's precisely the interpretation. It suggests these higher spin states are like the same quark system, just spinning faster, gaining angular momentum and mass in a somewhat regular way. It provides a powerful organizing principle for hadron spectroscopy.
That is neat. It puts the 72 and 92 states into a broader context.
It does. They fit into this pattern of rotational bands, if you like.
But again, for fundamental spin-9-halves particles, the theoretical problems are still there, maybe even worse.
Oh, absolutely. The issues with causality, unitarity, renormalizability become even more severe as you go to higher spins. There are no serious candidates for fundamental spin-92 particles anywhere near the standard model.
Okay, so we've covered 72 and 92. What about beyond? Pushing to 11 halves or even higher half-integer spins. Does the pattern continue?
Well, experimentally, it gets incredibly challenging. As you go higher in spin and mass, these resonances tend to get broader, meaning even shorter lifetimes, and their mass isn't precisely defined.
Harder to even see as a bump in the data.
Exactly, and the density of states increases. There are more possible excited states crowded together at higher energies, making it really hard to disentangle them. Plus, they might just be produced less often in collisions.
So the signals get weaker and the background gets noisier.
You got it. It's like trying to pick out a specific whisper in a roaring crowd.
But have people seen any hints of these even higher spins, like 11 halves?
There is some evidence, yes. The outline mentioned the 2950, which is listed by the PDG, with a potential spin of a 112 and positive parity. And there have been tentative claims, often from analyzing older pion nucleon scattering data, suggesting states possibly as high as 132 or even 152.
But these are pretty uncertain.
Very uncertain. Typically broad states with large error bars on their properties. But intriguingly,
They still fit the reg picture.
it seems so. Even these very high-spin candidates tend to lie roughly where you'd expect them on the extensions of those reg trajectories. It supports the idea that this pattern of rotational excitation continues to very high angular momenta within these composite systems.
Fascinating. Now, theoretically, when you get to these really high spins, the outline mentions string theory and holography. How do they enter the picture?
Right, so string theory is different because the fundamental objects aren't point particles, but tiny vibrating strings. Different vibrations correspond to different particles.
And higher vibrations can mean higher spin.
Exactly. In string theory, you naturally get an infinite tower of states with higher and higher spins as you go to higher vibrational modes. So a spin 112 particle, or N12 for that matter, could in principle exist as an excited string state.
But presumably at enormous energies.
Yes, typically at energies way beyond what we can currently probe experimentally, like the Planck scale, or maybe a lower string scale depending on the specific model, but still incredibly high. So it's more of a theoretical possibility for the very early universe or extreme environments.
Okay, so string theory allows them, but maybe not here and now. What about holography or add-SCFT?
That's a different, very powerful theoretical tool. It proposes a duality, a kind of mathematical equivalence between certain quantum field theories, like QCD potentially, in our normal space-time dimensions and theories of gravity or strings living in a higher dimensional space with a special geometry called anti-de Sitter space.
ADS.
A hologram where our world is the projection. Sort of, yeah. And in this framework, certain operators, mathematical objects representing physical quantities in the field theory, can correspond to actual fields or particles in the higher dimensional ADS space. And importantly, high-spin operators in the field theory can correspond to high-spin fields in ADS.
So it provides another theoretical playground where high spins appear.
Exactly. It's a very active area of research, trying to understand strongly interacting systems like QCD and maybe even quantum gravity using these holographic ideas. High-spin fields play a key role in these ADS theories.
But translating that back to definite predictions for elementary particles in our 4 dimensions is still tricky.
Very much so. And again, the fundamental issue remains. Constructing consistent interacting quantum field theories directly in our spacetime for elementary particles with spin greater than 2, whether half-integer or integer, is just notoriously difficult. Lorentz invariance, gauge symmetry, causality, unitarity, renormalizability, getting all these to work together for high spins is a major hurdle.
Okay. We focused heavily on the half-integer spins like 72, 92, 112. Does the outline mention anything about higher integer spins like spin 3 or spin 4?
It does, briefly. While our main focus was half-integer, it's worth noting that similar patterns and problems arise for integer spins beyond spin 2, the graviton.
Do we see composite particles with spin 3 or 4?
Yes, we do. There are known mesons particles made of a quark and an antiquark with spin 3, like the 1690 or the 1670. These are, again, understood as quark-antiquark pairs with significant orbital excitation.
So similar mechanism to the baryons, but with quark-antiquark instead of three quarks.
Right, and there are even spin 4 mesons observed, like the F2050. These also fit onto red trajectories.
But again, no known fundamental spin-3 or spin-4 particles.
Correct. And the theoretical challenges for massless elementary particles with spin 3 are very severe. There are some highly constrained theories, but nothing mainstream. For spin 4 and higher integer spins, it gets even harder.
But people are still working on the theory.
Oh, yes. There's a whole field called higher spin gauge theories, which tries to tackle exactly this problem. How do you build consistent theories of interacting elementary particles with spin greater than 2? Much of this work happens in the context of that ADS space we mentioned, using advanced mathematical techniques. Connecting it definitively back to particle physics in our 4D universe is still an ongoing challenge.
So high spins, whether half integer or integer, seem to be the domain of composite particles or very theoretical high-energy physics right now.
That's a fair summary of the current picture.
We talked about how the spin is determined using partial wave analysis, but could you recap how these resonances are actually produced and initially detected in experiments?
Sure. It starts with particle accelerators. You need high-energy collisions. This could be protons hitting protons like at the LHC, or electrons hitting positrons, or maybe fixed-target experiments like pions, or electrons hitting a stationary target like protons or nuclei.
Smashing things together at high speed?
Pretty much. In the debris from these collisions, you might produce these short-lived resonances. They decay instantly, as we said, into more stable particles like pions, kaons, protons, etc.
And you detect those stable particles.
Right. You use large, complex detectors surrounding the collision point to measure the tracks, energies, and types of all the outgoing particles. Then you analyze the data. A key technique is to calculate the invariant mass of combinations of these final particles.
Invariant mass? That's the mass the system would have if it were at rest, right? Independent of how fast it's moving.
Exactly. So if a resonance R was briefly formed and decayed into particles A and B, say, when you calculate the invariant mass of the A plus B system, you should see a peak or a bump in the distribution of those invariant mass values, right around the mass of the resonance R.
So a bump in the mass plot is the first clue that a resonance might have been formed.
Precisely. That's the initial discovery signal. Then comes the hard work we discussed, the partial wave analysis, to figure out the spin and other properties associated with that bump.
And which labs are doing this kind of work?
Several major facilities have contributed significantly over the years. Places like Jefferson Lab, JLab in the US, which focuses on electron scattering. Experiments at CERN, like LHCb, can study heavy baryon resonances. Basin in China does a lot with electron-positron collisions. And historically, places like Fermilab and Brookhaven National Lab, BNL in the US, also made key contributions. It's a global effort.
Okay, great. So let's try to wrap this up. This has been a really interesting deep dive. It seems the story of half-integer spin particles, 72, 92, and beyond is really about these excited states of composite particles, mostly baryons.
Exactly. They're not fundamental particles in the standard model, but they offer this fantastic window into the complex dynamics of quarks and gluons governed by the strong force, QCD. And concepts like red trajectories help us see a pattern, an order in this complexity, suggesting these are rotational excitations.
And the idea of fundamental particles with these high spins is mostly theoretical at this point, facing some pretty big hurdles.
Yes. Very significant theoretical challenges related to consistency principles, like unitarity and causality. String theory is one framework where they appear naturally, but usually at incredibly high energy scales, far beyond our current reach.
But even though they might not be fundamental, studying these high-spin composite resonances is still crucial.
Absolutely. Understanding the spectrum of these excited hadrons, their masses, spins, decay modes, is essential for testing and refining our understanding of QCD, the theory of how matter is built from quarks and gluons. It tells us about the structure of protons and neutrons in extreme conditions.
So as we close out, maybe a final thought for our listeners to chew on.
Well, maybe consider this.
Yeah.
We see this incredible complexity and structure, these red trajectories and high-spin states, emerging from the interactions of just a few quarks and gluons described by QCD. Could the patterns we observe in this particle zoo hold deeper clues? Perhaps about underlying symmetries or even structures of space-time itself that we haven't fully grasped yet at the most fundamental level.
Like the complexity we see is hinting at a simpler underlying principle we just haven't found yet.
Possibly. It certainly makes you think about how much more there might be to understand about the fundamental forces and particles that make up our universe. Maybe digging deeper into QCD or hadron spectroscopy or even just the basics of the Standard Model could spark some new connections for you.
A fascinating thought to end on. Thanks for guiding us through that complex landscape.
My pleasure. It's truly intriguing stuff.